what we did, of course, in the last 2 lectures, you saw the Fourier series, which is slightly different than the Fourier transformation. So Fourier series is a way to decompose a periodic function, to write it as a combination of sines and cosines, basically. And Fourier transformation is really is a way to make from one functions other functions, and they're intimately related, the Fourier transform and the Fourier series. But the setup is slightly different. In fact, if you recall, so the Fourier transformation, suppose you have some function depending on, say, t, then you can associate to it another function by integrating from -infinity to infinity, ft times e to the power minus I omega t dt. This is a function of omega. The t dependency disappears because you have integrated you integrate over t, and this is called this is some function f of omega, and it's called the Fourier transform of f of t. It depends on omega. So you take f of t, you plug it into this integral, you get another something else, and this depends on omega, and that's precisely what the Fourier transform is. So this is Fourier. And as you learned last year, it has to do also with decomposition, or it has to do with frequencies, etc. You can use it to analyze electronic circuits, etc. What I would like to do today is I like to have a look at what's called the Laplace transform, and it looks like this. So again, we have some function f. Then we can make the Laplace transform. For the Laplace transform, the variable s is commonly used. Of course, not necessary, but please do, because otherwise it will be a bit confusing. The Laplace transform is this. If you look closely, it looks very similar to the Fourier transform, with 2 major differences. First of all, we do not integrate from -infinity to infinity, but from 0 to infinity. And second, instead of I omega, we just have s. So s is here a real variable. In general, s can be non-real as well, but we will only, in this course, we will only consider the case that s is real. These differences have a few advantages. First of all, here the integrand is explicitly real. So this means that we only have to deal with real functions. Plus, if s is sufficiently large, then exponentials decay pretty fast. So in that case, this integral will actually converge. Convergence for the Fourier integral is much more tricky in general. And of course, we do not start at -infinity, but at 0 here. And as we will see, this will be very convenient for initial value problems where you have specified function values at t equal to 0. It will be very convenient, because let me stress this already here, that is what we will set out to do. We will use the Laplace transform ultimately to solve differential equations. How that works, I will not be able to tell you yet before the break. Before the break, we will just look at this definition and investigate some of its properties. And then after the break, I will show you how to implement, how to use this in the context of differential equations. Okay. So in principle, you can try this for any function. So let me just give a very simple example. Consider this example, ft is equal to t. And then the claim is that the Laplace transform is 1 over s squared whenever s is bigger than 0. Okay, so I would like to do this example in some detail because there are some subtleties that you have to take into account. So let me, for now, unshare my camera because I will be writing a lot. So we don't consider this anymore. We consider the Laplace transform. So what is the Laplace transform of f of t in this case? Well, we integrate from 0 to infinity, e to the power minus st times ft, dt, and in this case, we get e to the power minus st times t dt. This is the integral we have to evaluate. Now notice that this is an improper integral. So instead of integrating from 0 to infinity, what we do is we integrate from 0 to some number, say a. So we consider this integral 0 to a to the power minus st times t dt. This certainly converges for all values of a, and then at the end of the story we take the limit of a to infinity. All right. Now, I'd like already to distinguish two cases. First, I will assume that S is non-zero. So we assume for S is non-zero. Then we can use integration by parts. So we get this times the antiderivative of this, t times antiderivative of e to the power minus st. What is that? That is 1 over minus s e to the power minus st between 0 and a. Note that we had to exclude the case s equal to 0 because I'm dividing by 0 here. So we'll do the case s equal to 0 later on. Minus the integral from 0 to a. This times the derivative of that. So that's 1 divided by minus s e to the power minus st. All right. So this minus and this minus we can make into 1 plus. So let's do that. And then we can integrate this again. I'm leaving this here for now.
Just put dt under the integral. So
thank you. And then second antiderivative here. So another 1 over minus s. So we get actually 1 over 1 divided by minus s squared e to the power minus st 0 a. Okay, now we can plug in the upper limit and the lower limits at both cases. So the upper limit here I get a times 1 divided by minus s. So please note that t was the integration variable, so I have to plug it in at positions of where the t occurs, minus sa. Plus, sorry, and if I plug in 0, of course, because get t equal to 0 here, I get nothing. And here I get
but in that case, you have 1 over s squared, not minus s squared, right? Because you have minus s and then you have integrated and you have again minus s.
Yeah, but I took the minus s and the minus here. I made it into 1 plus.
Right. But after the second integration, under that row.
Yeah, but a minus s comes down, so I get a minus extra minus s here, right?
Yes.
It's correct, I think.
Yeah. Okay. Sorry. Yeah. Okay. So you. Yeah. Sorry.
Okay, great. Good when we agree. Minus s squared, and then I get e to the power minus sa here. Minus, so plus 1 over s squared. Now there's a plus because and if I plug in 0 here, t equals to 0, I get 1, so I get this 1 over minus s squared e to the power minus sa plus 1 over s squared. I don't have to put those here actually. Okay, so now what happens if we take the limit for a to infinity? Let's have a look. So if a goes to infinity, well, if s is negative, I get here e to the power something positive, minus s is positive, so I get positive times a, and a is positive as well. As a goes to infinity, this will explode. This will go to infinity. Same here. This will go to actually, let me write it maybe because no, it's correct. Sorry. So here I get this goes to infinity. This goes to infinity because of the minus signs. I get minus infinity, and a goes to infinity, so I get minus infinity. Does that make sense? Is there a mistake somewhere? If s is negative, yeah, right. If s is negative, 1 over minus s is positive. Yeah. So this is positive, this is positive, this is positive, so I get plus infinity. All right. Sorry. I was a bit confused by the minus signs. Easy to get confused by the minus sign. So I get plus infinity if s is smaller than 0. Everything here goes to infinity. This 1 over s squared doesn't matter anymore. This blows up. If s is bigger than 0, then this will go to 0. Even though I multiply with a here, which goes to infinity, the exponent will win. It goes to 0. This goes to 0, so I get 1 over s squared. The only case that I have to consider yet is the case that s is equal to 0. So what do I have then? Well, integral from 0 to a. If s is equal to 0, e to the power st is 1. So I get just this integral. This is, well, 1/2 a squared minus 0. And if a goes to infinity, this goes to infinity. So you see that I get infinity if s is smaller than or equal to 0. So then the Laplace transform is not defined. But for s bigger than 0, I get this. I get 1 over s squared. Right. This is the idea. This is it, basically. This is how you do these evaluations, how you do these calculations. My question for you is try this for yourself for the next, say, 2 to 3 minutes. Try yourself these two. And please try to write down for which values of s the Laplace transform is actually defined. So have a look at these two for, say, the next 2 to 3 minutes. Try it yourself, and then we will discuss the outcomes. Okay, because of time, let's have a short look. Okay, so there's still some questions in the chat, but I'd like to continue with this example. So first of all, let me give the answer for both. So we get the Laplace transform of e to the power 5t is 1 over s minus 5, and s has to be bigger than 5. And Laplace transform of gt, sorry, I put it on the previous slide, is precisely this. So you have to make this distinction between S0 and S non-zero, and it actually works for all values of S. So about the first one, quick poll. Which one applies to you? Okay, 5 more seconds. Okay, so quite a lot of those who voted did get the right answer, but also still got something else or weren't done yet. So let me, because there was some questions also about this improper integral. So always write this, right? If you have the integral from 0 to infinity, ft times e to the power s. So here we have e to the power 5t times e to the power minus st dt. This is the Laplace transform. It's an improper integral. Always use limits to evaluate this. So this is the limit of a to infinity of 0 to a e to the power 5t e to the power minus st dt. And now what you see, actually you can already see that here. If you rewrite it to 0 to infinity, you can take those two together. E to the power 5 minus s times t dt. You see that if s is bigger than 5, then this is positive. This means that the exponent is increasing and that the integral will be divergent. You can also do this using the limit, but you can actually already see there. If your integrand is increasing, is positive and increasing, then this integral cannot converge. Also, if s is 0, if s is equal to 5, then this is 0. What happens then? Then it's just a function 1. That's also, in that case, it also doesn't converge.
But I'm sorry, but if s is bigger than 5, then the exponential
Smaller than 5, yes, thank you. Oh man, yeah, sorry. If s is smaller than 5, then this is bigger than 0. Everybody agrees with that? Okay, thank you. Great. Yes, thank you, Katerina. Yeah, so this is then positive. So then the integrals, but then the integral is divergent because the integrand is increasing, and the same if it is equal to 0, then the integral is also divergent because it's 1. So from this, I can already tell that we only have to consider the case where s is bigger than 5. For s bigger than 5, the integral is of course the same. Well, it's just 1 over 5 minus s e to the power 5 minus s times t, 0 to a. This is if I plug in, so 1. And there I get e to the power 5 minus s times a minus 1, if I plug in 0. And now you see that if you take a to infinity, because I assumed s bigger than 5, 5 minus s is negative. So this will go to 0. So in the limit, of a to infinity, I'll write it like this. If a to infinity, this goes to 1 over 5 minus s times 0 minus 1, which is 1 over s minus 5. That's Laplace transform in this case. Okay. So this is important, that it only works for certain values of s. Now the second one, maybe first a quick poll. I'm curious who actually, how many of you had the answer here? Yeah, okay. I can understand that most of you weren't done yet, so let's have a look at it in some detail. Yeah, okay. I get a picture. So note, what's important here is to remember what the function is. GT was 1 for t between 3 and 7 and 0 otherwise. Let me make a short peek. So the point is that it's nearly only between 3 and 7, this function is non-zero. So the graph looks like this, right? So it's 0, 0, and then at some point at 3 it jumps up, and then here it jumps down again. That's the function. So only in this regime, my integral, it contributes to the integral. If you look at the integral from 0 to infinity of gt e to the power minus st dt, well, this is 0 except between 3 and 7, so I can just write the integral from 3 to 7, and there it is 1, so this is just, the function is 1, it's 1 times e to the power minus st dt. This is equal to that. But this is no improper integral anymore. You don't have to consider any limit, actually. So we can just evaluate this. It actually converges, it exists for all values of s. Still, I have to make a distinction, because if, let's first look at s non-zero, then this is simply 1 over minus s e to the power minus st between 3 and 7. So I get e to the power minus 7t minus e to the power minus 3t divided by minus s, which you can rewrite to what's here on the slide. Of course, this only works if s is non-zero, because you divide by s. So for s equal to 0, you have to make a separate consideration, but then this function is just 1. So we get the integral of 1 from 3 to 7, that's 4. So this is my function here. This is the Laplace transform. Okay. What I would like to do now is, so in principle, you can do this for many, many functions. And I want to have a look at some of the standard functions. This is a table actually that I will give now that will also be available. That's also in the book, so it will also be available on the exam, and you are allowed to use it. And more about that later. So in general, if you have t to the power n, then the Laplace transform is n factorial divided by s to the power n plus 1. We have seen the case n equal to 1, and you see that it works out. You get 1 over s squared. Well, there's the sine and the cosine. Those are very similar. You get expressions like this. You can do this calculation. It's a lot of work. You have to do this magic trick. I forgot what you called it. So you get some exponential times the cosine. You have to do this partial integration by parts twice, and then you can pull it to the other side and you get an expression. I know Foucault had a name for this. It was something like super trick. I always forget, but I guess you remember. For e to the power ct, you get 1 over s minus c. We saw the case with c equal to 5. Oh, I forgot to write the values. This is for c bigger than, for s bigger than c. I'll put it there on the, let me do it. Put it here. So in this case, you get, this is for S bigger than C. And the last one is useful in some cases. If you have e to the power ct times some function g, then the Laplace transform of this, so of g times e to the power ct is simply the Laplace transform of g, but not evaluated at the point s, but at the point s minus c. And you can actually write that down immediately. So the Laplace transform of ft, by definition, is the integral from 0 to infinity of ft, which is e to the power ct gt to the power minus st dt. This is 0 to infinity gt. And I can take those two together, e to the power minus s minus c, I get minus minus because I have a plus here, times t dt. And this is exactly the Laplace transform of g, but not at s, but at s minus c. So this is the Laplace transform of g at s minus c. We'll see an example of this later on, how you can use this. So the book goes more in depth about the convergence that I just mentioned. So you should be aware that this convergence can be an issue. The book identifies types of functions for which Laplace transform works. I want to focus in this lecture on the applications and the main properties and the applications. So I will not go into depth that much on this. So okay, we can take Laplace transforms of functions. Very nice. But there's more. This Laplace transform actually has very nice properties, very similar, by the way, to those of the Fourier transform. First of all, if two functions are different, then the Laplace transforms are also different. That means that the effect of a Laplace transform is invertible in some sense. So if one function can only have one, so if you know the Laplace transform, there can be only one function that has this Laplace transform. You cannot have the two different functions have the same Laplace transform. So in principle, if you know the Laplace transform of a function, and you know the function itself, the Laplace transform fixes the function itself. This is called injectivity. I'm not going to prove it here. It's actually.
But, I'm sorry, there is a typo in the second Laplace transform. We have.
Oh yeah, there should be a 2. Thank you. That's weird, right? They should be equal if the numbers are equal. So this is a 2. Yeah, I'll fix that one as well. I have to make notes about the typos. Okay. So this one is actually not that easy to prove. I will not prove it, but it's important is that if you know the Laplace transform, then in principle the function itself is also fixed. All right, Laplace transform is linear. This is very nice because this way we can build Laplace transforms from Laplace transforms that we already know. For example, if you have the Laplace transform of 2 times the sine of t plus the cosine of t. Well, by the table, we know the Laplace transform of this and that. So we get 2 times the Laplace transform of the sine, which is 1/1 plus s squared, plus the Laplace transform of the cosine, which is s divided by 1 plus s squared. So in that way, you can simply take these linear combinations. That's very nice. And this is just where you can just write it out. It's a direct consequence of the linearity of the integral, sum and some rule for integration. And then this one is really important. This one is what we will use to solve differential equations, actually. The Laplace transform is of a derivative, can be expressed of a function, can be expressed in the Laplace transform of the function itself. How does that work? Of course, here I am assuming that all functions are nice in such a way that the Laplace transform exists. That's an overall assumption here. So how does that work? Well, basically, it's an integration by parts where it comes from. So let's assume that Laplace transform of f exists. So let's assume that this one But it converges, right? Then what about this one? Well, let's have a look. It's just by definition, it's this. And of course, I have to take this limit, right? So I rewrite it as a limit. Integral 0 to a f prime of t e to the power minus st dt. Okay. Now I'm going to do integration by parts to get rid of the derivative. So I get the antiderivative of f prime, for which I can just take f times e to the power minus st minus integral from 0 to a of ft times the derivative of my exponent. So I get ft times e to the power minus s derivative with respect to t. So I get a minus s here as well. This is between 0 and a. Okay. So let's see. What do we get? Let's write it out. So we get the limit of fa times e to the power minus s a minus, we plug in 0, so we get f0 times 1. We get minus minus. This s is not a variable in the integral, so I can pull it out. That's important. So I get plus s times integral from 0 to a ft e to the power minus st dt. This has to go to 0. Why? Because we assume that this integral is convergent. If this wouldn't go to 0, this cannot be convergent. So this goes to 0. This is just f0. And if I take a to infinity, I get this integral from 0 to infinity of ft times e to the power minus st. That's exactly the Laplace transform of f. So I get minus f0 plus s times the Laplace transform of f itself. That's exactly what's written here. So instead of differentiating, we can just multiply with this s. All right. And this I can repeat. I can. The most general version is this. So more generally, we have that the nth derivative of f can be expressed in the Laplace transform of f itself, minus a whole bunch of the values of f at the point 0. And you already recognize here the boundary, the initial conditions that we will see later on. So just how do you prove something like this? Well, you can just do it inductively, really. So what you could do, for example, is I can just write, I can just use the rule above repeatedly. So I can do this, for example, f double prime of t at s. What is that? Well, according to the rule here, it's s times the Laplace transform of this s minus f prime at 0. So I apply this rule with f prime instead of f. Then I apply the same rule to this. So I get s times the Laplace transform of f itself minus f0 minus f prime 0. So I get s here also. There's an extra s here. So I get s squared times the Laplace transform of f minus s times f0 minus f prime 0. So this way you can construct this whole thing. One moment, please. All right, sorry about that. Okay. So well, I can already tell what we will be doing. If you take a differential equation, then there you have a combination of a function, a derivative of function, and a function itself. If you take the Laplace transform of the differential equation, then after transforming, there are no derivatives anymore. Then you can simply solve the function. This way, you can easily find the Laplace transform of the function. So that's actually the relatively easy part. The hardest part then is to transform back. You remember maybe from Fourier that there is an inverse Fourier transform, and it's actually very similar to the Fourier transform itself. So then you have to integrate, find another integral, and then you can find the inverse. For Laplace transforms, there is an inverse, but it's hard to write down, given the amount of mathematics that you have seen at this point. You can write it down, but you will need more complex function, complex analysis, the theory of complex functions to write it down properly. So what we will do is we'll use the first part and the fact that we have a table. We have a table where we know that a bunch of functions we know the Laplace transform. So if we recognize in our Laplace transform those functions, then we know how to go back by this property, right? Because any function can only have one Laplace transform. So this will be the main trick, to calculate the inverse Laplace transform by using the table. And I will give you an example of how you could do that. So I want to focus on that first, and then after that we can apply the full setup in the context of differential equations. So let's have a look at this this function. So this is not in my table. So maybe you could, if you have downloaded the slides, then you can scroll to the tab where there is where the table is that we saw. I can no, not this way. I can go there now. So this is the table, and our function was, let me copy it on 1 divided by, so f of s is 1 divided by s plus 3 squared plus 4. All right. What can we do? Well, this is our table. How can we use it? Well, it looks similar to the Fourier transform of the sine, right? There's something squared, something constant. Of course, this would be then my a squared. There's no a, but I can easily write it like this. I can write it like 1/2 times 2 divided by s plus 3 squared plus 4. If this were only s squared, then this would be the Fourier transform of sine 2 times t. But it's not. There's the s plus 3 here. There's a shift. So I have a shifted Fourier Laplace transform. And this is where this last thing comes in. I can write this as g of s plus 3, where g of s is 1/2 times 2 divided by s squared plus 4. This is the Laplace transform by the table, right? This has to be the Laplace transform, and by linearity, so this factor 1/2 doesn't matter. It's just 1/2 times the sine of 2t at s. So you see that for this capital G, we can find the inverse Laplace transform. Sine of 2t will give me the 2 divided by s squared plus 4, and the factor 1/2, because of linearity, is just 1/2 times the Laplace transform. This is of G. I need the Laplace transform of f. So I know that f of s is the Laplace transform of this function, but not evaluated at s, but at s plus 3. You see we're now in the situation here where gt is 1/2 times the sine of 2t, and c This is minus c. So c is equal to minus 3. So it says that this whole thing is equal to the Laplace transform of g times e to the power ct. So this is the Laplace transform of e to the power minus 3t times 1/2 times the sine 2t at s. So this is the ft I'm looking for. My capital F is the Laplace transform of this function. So you see how we can combine several points in this table to find inverse Laplace transforms. And this shifting is an important trick. So please, that's why I showed this example, because this occurs also in the homework and also in practice. You see this a lot. So you have to do this shifting. The shifted version of a Laplace transform always indicates that there's some exponential at the original function. Multiplying with this exponential corresponds to shifting in the Laplace domain. So this is how you can use this. All right. That's the idea. So we write capital F is capital G of s plus 3. Oh, I chose here the so the 1/2 times 2 divided by s squared plus 4, and then we know that this is a Laplace transform of 1/2 times the sine, and because it's shifted, I know that small f has to be this times some exponential, and the right exponential in this case e to the power minus 3t. That's the idea. Okay. Now, please. So we have a break. After the break, I would like to discuss those. So let's have a break of 50 minutes, but meanwhile, just try them, just have a look at them. So the trick is those functions are not in the table, but my claim is they can be rewritten in such a way that you can use the table to find the inverse Laplace transforms. So we'll come back to this in 50 minutes, and if you like, you can have a look at this already. Okay, everyone, let's continue. So there was a question Marissa asked, do we really have to do this during the break? So yeah, my question was just have a look at it. We'll discuss. I will discuss though. I'm curious whether you did find the answer. So I will just give you the answers and then we'll discuss this. So about the first one, so this was the 1 over s squared plus 4s plus 5. So I'm curious, anyone found it? All right. Stop it now. Okay, yeah. So let's see that some of you actually did find it. Many of you say I wasn't done yet. Well, it was also a break, so I can't really blame you. Let's have a look. So we don't have anything like this in the list. What you can do here, so there are several techniques that, so I chose these, of course, these examples to discuss those techniques. So the whole point of this this trick is to this part is to rewrite the function in terms of s in the Laplace domain in such a way that we can use the table, this table, and the linearity of the Laplace transformation to transform back. That's the whole point. So we do need to do some rewriting because this is not in the list. One idea is you can try to get rid of the linear term. How do you do that? Well, completion of the square. Remember? So this is 1 over, I can write it as s plus 2 squared. If you do that, you have the s squared here. You get 2 times the cross term, so you get 4s, but you also get plus 4. I can subtract that. And then I can, of course, plus 5, still have the plus 5. So I can then rewrite this as 1 over s plus 2 squared plus 1. And now you see this is very much like the Laplace transform of the sine, but not at s, but at s plus 2. So we can write this actually as the Laplace transform of the sine of t, but not evaluated at s, but at s plus 2. See? But the Laplace transform of the sine is sine of t. If a is 1 over s squared plus 1. But I don't evaluate it at s, but at s plus 2. So we need this shift again, just as I did before the break. So this is my gt, and this is the c, minus c is this, so c is minus 2. And so this is equal, by the last rule here, to e to the power minus 2t times the sine of t at s. So the inverse Laplace transform of this, so now it's evaluated at s, so that's what I want. So my ft is really e to the power minus 2t times the sine of t. So that's a trick. Completion of the square is one trick. Next one. Exactly the same, almost the same, sorry, not exactly the same. Oh, but now there's a minus 5. Right. So the claim is you get this as a result. Anyone who found that? All right, I get an idea. Only very few found it. Yeah, so let's see what we get here. So again, you could try to do completion of the square, of course. Then we get 1 over s plus 2 squared minus 4 minus 5. I get this. Something like this with a minus sign is not in my list. You can make a list where it does occur, but it's not in the list that you have that I just showed. The question is, what can we do here? Well, there's another trick we can do. So this one is new. Please pay attention. We can factorize this. Let's see. So what do we get? We get s plus 5 times s minus 1, like that. That's a factorization. This is also not in my list, of course. But now comes the trick. If you remember from last year analysis, first year's analysis, you can do a partial fraction here. You can split this into two parts. A divided by s plus 5 plus b divided by s minus 1. What should a and b become? I'll just write them as one fraction again. You get a times s minus 1 plus b times s plus 5 divided by the product. So we find that this has to be 1. Well, I can rewrite this as an a times s and a b times s. So I can rewrite this as a plus b times s minus a plus 5b. And this should be equal to 1 for all s. This is the same as saying, actually, that I don't want any s dependency. So a plus b should be 0. And minus a plus b, 5b, should be 1. Well, you can solve this in your favorite way. You will find that a is minus 1 over 6 and b is 1 over 6. It's just a linear system, right? So this is a trick. So actually, so wrapping things up, we can write that this s plus 5 s minus 1 is equal to minus 1 over 6 times 1 divided by s plus 5 plus 1 over 6 times 1 divided by s minus 1. That's what we find. And those two, those are in my list. Namely, here. Brackets are not really necessary. So it's 1 divided by s minus c. So this is the Laplace transform of minus 1 over 6. The s, this is the case where c is minus 5, so this is e to the power minus 5t plus 1 over 6 times e to the power t, the case where c is equal to 1. And here you find your function. Oh, that's too fast. So you get this answer. So the important thing here is partial fractions. Those play an important role in this inverse Laplace transform. So if you forgot about them, please look them up in your last year's lecture notes. So there's plenty of examples in the book, by the way, so you can also study those. But you should be aware of this integration by parts. So no, not integration by. So this partial fraction technique. But this is the most basic case. We will see a more complicated one later on. Then the last one. Let's check again. Okay, I got an idea. Yeah, so you can do this in several ways. So what was the function again? It was s divided by s peak plus 3. Okay. Well, actually the easiest way to do this one is to note that we have, of course, 1 over s squared in the list, right? For this case, for n is equal to 1. We also have, well, it's basically a shifted version of 1 over s squared, right? So you probably get something with an exponential in it. But then there's this s. How can I get rid of this s? Well, there's one trick that I would like to show you here, and it's this. I can add 3, and I can subtract 3. And I get s plus 3 divided by s plus 3 squared minus 3 divided by s plus 3 squared. And now we're really done, because this is 1 over s plus 3. We get minus 3 divided by s plus 3 squared. So 1 over s plus 3, that's the Laplace transform of here, n equal to 0. 0 factorial is 1, remember? Divided by s to the power 1, so we get 1 over s. So it's 1, but not evaluated at s, but at s plus 3. There's a shift. But by the last rule, this is equal to the Laplace transform of e to the power minus. Oh, what am I doing? I can also use this rule, right? Okay, sorry, this was a bit, okay, so it's nice it's all consistent, but you can also just use this rule, sorry for that. And then the minus 3 divided by s plus 3 squared, that is the Laplace transform of minus 3t, but evaluated at s plus 3. And because of this shift, we now do invoke the last one. This is equal to the Laplace transform of minus 3t times e to the power minus 3t at s. That's what this last rule tells us. So the whole thing is a Laplace transform of this plus that. So 1 minus 3t times e to the power minus 3t. So this is the function that we were looking for. That's the idea. So you need some techniques to do this rewriting. Partial fractions is one of them. We will see a more complicated example of a partial fraction in a minute, and also in the homework you will see it. So please look up those techniques from last year. This is the most important one, and sometimes you have to do you can do tricks like this. All right. What I would like to do now, so now we can do this. So we now know how to calculate the Laplace transform. We know that there's a table, so that's convenient. We can use that. We know that we can go back, although we will have to do some rewriting. Now I would like to show you how it works how you can apply Laplace transforms to solve differential equations. And I will just walk you through one example to illustrate this. In fact, we're not only solving the differential equation, but we're solving the entire initial value problem at once. So let's have a look at this one. Okay, so in principle, we have all the techniques necessary to solve this. You could actually last year you could already solve this, but now let's use this new technique to do it. So my claim is, first step is transform both sides. First of all, the Laplace transform.
Bart, move please the paper to the right.
Yeah, sorry.
Yes, like this. Thank you.
I think my camera slid a bit. So yeah. First of all, the Laplace transform of this will occur many times. I'll just give the name capital Y of S for convenience. The Laplace transform of the second derivative. What is that? Well, we had this rule. by this rule, this was the Laplace s squared times the Laplace transform of y itself minus s times y at 0 minus y prime at 0. So I can just write this as s squared times capital Y of s. Y0 is given, it's 2 minus 2s. Y prime is given, it's 0. So we get this. So the Laplace transform of the left-hand side is simply s squared capital Ys minus 2s plus 9 times capital Y of s. All right. That's the Laplace transform of the left-hand side. Laplace transform of the right-hand side, e to the power minus t. What the s here? What is that? Well, we can just use the table. Let's have a look. It's this one with c equal to -1. So and times 5, so I get 5 divided by s plus 1, right? Okay. Right. Now, then we have to equate those because left-hand side is equal to right-hand side. So we get that s squared capital Y s minus 2s plus 9 times capital Y s is 5 divided by s plus 1. That's a transformation of both sides. Great. Now, this is no longer a differential equation. It's an ordinary equation and we can simply solve it for y. That's the next step, solve it for y, capital Y. Well, we can take this to the other side. We have s squared plus 9, so we get s squared plus 9 times capital Y of s is equal to 2s plus 5 divided by s plus 1. Actually equivalent. Capital Y of s is 2s divided by s squared plus 9 plus 5 divided by s plus 1 times s squared plus 9. All right. That's it. That's the Laplace transform of our solution. It's really as easy as that. So it's really easy to find the Laplace transform of the solution. Of course, we have to go back now. So this is the most difficult part, usually, transforming back. So let me have a look at the table. Here's an s squared plus 9. Well, 9 is 3 squared. And there's an s, so this very much looks like this cosine, right? So this first part, I can write it as 2 divided by 3. Sorry, I don't need it. Sorry, it's 2 times s divided by s squared plus 3 squared. That's what I wanted. And this is just the Laplace transform of the cosine. So we know how to transform this back. This is the Laplace transform of 2 times the cosine of 3t. Okay, that's very nice. But what about this? You see a product in the denominator. I don't have anything like this. Of course, I have something with s squared plus 9, sorry, in the denominator, and I have something with s plus 1 in the denominator, but not the product. So again, here we will split the fraction. We do apply partial fractions. So let's have a look. So how does this work again? I want constants like this. So this would be a first reaction, what I see many people do, right? You want a and b to be constants, but this is not going to work. And why not? Because if you multiply, you get a times s squared, but you get no other terms with s squared involved. But there is no s squared on this side, so you somehow need extra terms to cancel the s squared. Because if you would leave it like this, you write a times s squared, then that should be 0. Then a has to be 0, so you're left with this, and you will never get it equal. The trick is, so it's always the case with partial fractions. If you do it like this, then make sure that the thing you have in the numerator has degree 1 less than the thing in the denominator. So like this. So we introduce a new unknown constant. And now we can try to pull everything back together and see what a, b, and c have to be. All right, so we get a times s squared plus 9a. Here we get s plus 1 times bs plus c. So we get s times bs, so that's plus b, s squared. That's good, because we wanted s squared to be cancelled. Then we get 1 times bs. We get s times c, so plus c times s. And we get 1 times c plus c. This has to be equal to that. So this has to be equal to 5. Well, we can write this a bit nicer. We can write this a plus b times s squared. Here's b, s, and cs, so plus b plus c times s. And here we get 9 times a plus c, so plus 9a plus c. This has to be 5 for all values of s. You can only make this work for all values of s if this is 0 and this is 0 and this is 5. So we get 3 equations. A plus b is 0, right? B plus c is 0. And 9a plus c is 5. Okay, so you can solve this in your favorite way. Actually, you see here is b is minus a and c is minus b. So a is equal to c. C is minus b. That's what follows from these two. And then 9a plus c, so 10a is 5. So a is 1/2. B is minus 1/2. And c is 1/2. So that means that we can write this whole thing as 1/2 times 1 over s plus 1 minus 1/2 times s divided by s squared plus 9 plus 1/2 times 1 divided by s squared plus 9. And now I'm in good shape because this is in my Laplace table, right? Over here. This one is in my Laplace table. It's a Laplace transform of a cosine 3t. This one is almost in my Laplace table. If I write a 3 here and then divide it here, so divide by 6, then it's sine of 3t. This whole thing is the Laplace transform of 1/2 times e to the power minus t minus 1/2 cosine 3t plus 1 over 6 sine 3t. And then I can put everything together. So let me put it on the slides. We transformed both sides. We solved for y. We find capital Y of s equal to this plus that. Then, well, the first term is, there's a typo. It should be an s. Like that. And then this whole fraction, by using these partial fractions, we found that this whole thing is 1/2 times 1 over s plus 1 minus 1/2 s divided by s squared plus 9, 3 squared, plus 1 over 6, 3 divided by s squared plus 3 squared. And all these terms up to the factor occur in the table. So now I can transform back. You get this 2 times. So this first one, of course, this should be s. S divided by s squared plus 3 squared to get 2 times the cosine. Here I get e to the power minus t. Next one, minus 1/2 times the cosine 3t plus 1 over 6 the sine of 3t. This is the solution. And I did at no point did I use one of the techniques that we've seen before. We did not solve a characteristic equation or something. We just took the differential equation, transformed it, and the nice thing is that we just could take the initial value conditions along with it. So we actually solved the whole boundary, the whole initial value problem in one go, and that's very nice in this case. So that's a nice thing about the Laplace transform. You don't have to do all these separate stages where you first solve the homogeneous equation and then find a particular solution of the inhomogeneous equation, and then at the end have to plug in the boundary conditions. No, it all works out in one attempt, really, one calculation. So that's a very nice property of the Laplace transform. Of course, there are some things that are well, not as easy as you would like, maybe. And the main thing is this rewriting. That's usually the most difficult part. The transformation is more or less automatic, and then the rewriting requires a good command of the technique of partial fractions, but also some creativity sometimes, as in the example that I showed, one of the examples from the exercise before the break. When it comes to the partial fractions, the main things that you have to remember is this one. So you can always decompose it like this, but make sure that in the numerator, that the thing that you put there has a degree 1 less than the denominator. If you omit this, then it might not work. You might find no solutions there. So just be aware of that. Right, and there's plenty of opportunity to practice this in the homework, and we'll see examples of it later on as well. Okay, let's see what the status is for the questions at this point. Okay, that's answered. Never mind. Okay, that's great. What I would like to do in the remaining time is have a look at what's called step functions, because you might wonder why we care about Laplace transformations if we can only do things that we already could do, maybe in a slightly more elegant or convenient or easier way, but still we were already able to solve equations like this. The good thing about Laplace transforms is that it really they work very nicely with step functions, discontinuities. So let me explain. Let me give an example of a practical situation where you might encounter something like that. Suppose we have an RC circuit. That the resistor.
Part is not visible. A little bit. Yeah, okay. Like this.
And a capacitor. And here we split the track, and there's a battery, and there's a switch. So this is a switch. Well, let's say that the resistance is the resistor. What did I have in mind? Is 1, and capacity is 1/2 farad. That's very large, but yeah, I like nice numbers. And let's say that this is just an external power source. Let's say it's 5 volt. Right. If let's say that we look at the amount of charge on the capacitor, so Qt is the charge on the capacitor. And the total voltage here, that's Q divided by C plus the current times R. The current is the derivative, change of charge, so that's Q prime times R. So that's Q plus Q prime. And this is equal to, well, if the switch is like this, then it's 0. But let's say that at some time, let's say t equal to 3, we pull the switch. And for t smaller than 3, it's 0. And for t bigger than 3, it's 5. Okay. This is a differential equation. But and maybe let's turn it into an initial value problem. So let's say that Q0 is equal to 1 coulomb. This is a differential equation. And we can, of course, try to solve it. But the problem is that this right-hand side is discontinuous. But as we saw before the break, in the very beginning, it's very easy to calculate Laplace transform of a discontinuous function. We can just do that. We actually did it already, right? You already did it with this function that was only 1 between 3 and 7 and 0 otherwise. It's a discontinuous function. It's 2 jumps. And you can just take the Laplace transform. So we can look at what happens in the Laplace domain. Of course, then we have to transform back as well. So to do this properly, I need some more notation and some more results that are related to these discontinuous functions. So that's what I would like to do. I would like to have a look at step functions. It's section 6.3 in the book. First of all, what's the definition of a step function? So first I will develop some theory and notation, and then we will try to solve this problem if time permits. Okay, so we start with the definition of what's called the unit step function, or it's called a Heaviside function. Maybe you already encountered it in, I don't know, electronic instrumentation, for example. Otherwise, I guess you will. Did you already see this, by the way? Heavisides or step functions, you have seen it? Okay. Yeah, okay, good, great. You've already seen it. That's nice. Now you see it again. So what is it? It's a function that is 0. So it makes a step at c of size 1. So you have the graph is really, if c is positive, it goes up to here, and then it jumps up. So this is t equal to c, and the height is 1. This definition, what exactly the value is at t equal to c, well, there are different conventions. Some take it to be 0, some take it to be 1, some take it to be 1/2. All kind of makes sense. It doesn't really matter for our analysis. That's why I omitted it here. So this is already a very nice function because you can rewrite the this 2q plus q prime is equal to 5 times u at 3 of t. So you can write it really compactly. We'll see next time more examples of this. So often you have these functions that are piecewise defined. Using the step function, you can simply write it in a very convenient, very condensed way. So that's already one advantage. Okay, let's go on. So this is just a definition. What is the Fourier transform of the unit step function? Well, it's this, e to the power minus c times s divided by s. It's actually not very hard to find that. Let's have a look. So integral from 0 to, let's do from a, and then at the end take a to infinity. Let's take a bigger than c for now. uc of t times e to the power minus st dt. So I'm calculating the Laplace transform here. What is this? Well, this is 0 if t is smaller than 1 and big, and 1 is smaller than c, and 1 if t is bigger than c. So, and since we assume a to be bigger than c because we're taking the limit of a to infinity anyway, we can just take c to a of e to the power st dt. And this is equal to what? Well, it's 1 over minus s e to the power minus a times s plus 1 over s e to the power minus c times s. And if s is bigger than 0, and you take a to infinity, then this goes to 0. So we get 1 over s e to the power minus cs. Okay, so you can easily calculate this yourself, actually. This is the Laplace transform. All right. So we also know that if we encounter something like this, then the inverse Laplace transform is a unit step function. Okay, we're almost there to do the. So we can now, in principle, find the Laplace transform on this side of this equation, right? Let's do that. So let's write the Laplace transform of Qt as let's just write it as capital QS, just for convenience. Then the Laplace transform of Q prime of t. What is that? Well, that's S times the Laplace transform of Q minus Q0. So we defined Q0 to be, you chose Q0 to be 1, and this is Q, this S times QS. So that's this. So if I plug this into my differential equation, I get 2 times QS plus S times QS minus 1 is 5 times the unit step function with C equal to 3. So this is 5 times e to the power minus 3s divided by s. And this I can rewrite. So qs is equal to, I get 2 in s, so I get 1 divided by s plus 2 plus 5 times e to the power minus 3s divided by s times s plus 2. Okay. Now, if you looked in the table, so this I can transform. I could just get an exponential decaying function. That's okay. But here, I don't have anything with exponentials in the Laplace domain yet. So how do you transform this back? Well, that's where the following theorem comes in. This is a very convenient one. So if f and g, we assume that f and g are nice in the sense that the Laplace transforms, Laplace integrals actually converge. Then the following is true. If the Laplace transform of a step function times a function f is e to the power minus s times the Laplace transform of f plus t plus of the shifted f times s. There's a shift here. And if we replace f of t plus c by g of t, then we get the following. So if we write this here as gt, then f of t is gt minus c. And you get that the Laplace transform. So this one is convenient if you want to go from Laplace domain back to the t domain. If you have e to the power minus sc times the Laplace transform of some function, then this whole thing is the Laplace transform of step function times the shifted g. That's what I can use here. Let's focus on this term here. So before proving why this is true, I will just show you how you can use it. Let's focus on this. So we can write this as 5 times e to the power minus 3 times s times 1 divided by s times s plus 2. So we have now something of this form, except for the factor 5, but that's just an overall constant multiplication. This is precisely of this form. If I can write this as the Laplace transform of some function g, then I can find the Laplace transform of the whole thing, including the e to the power minus 3s. To do that, let's split the fractions here, because this is not in my table, but you can split it. I'm not going to do the details here. You can try this yourself. I have to peek. What did I find again? Oh yeah, it's 1 over s minus, 1 over s plus 2 times 1/2. So I can put the over 2 here. So this is what this is. You can check yourself. This is the Laplace transform of what? Well, it's 1 over s, so that's 1 minus e to the power minus 2t, according to the table. So this is my g of t. So the whole thing, 5 over 2, no, let's first do the exponential. So e to the minus 3s times this thing. This is e to the power minus 3s times the Laplace transform of this gt. So according to this rule on the slide, this is equal to the Laplace transform of the step function, which jumps at c equal to 3, times t at evaluated at g evaluated at t minus 3. So what is that? It's the Laplace transform, the unit step function, times this thing. What's that? Well, it's this function evaluate, but now t minus evaluated at t minus 3 instead of t. So I get times 1 minus e to the power minus 2 t minus 3 times s. That's what it is. All right. Wrapping everything up. So we had this, the Laplace domain. We rewrote it as this. There's a factor 5 missing. Let's put it there. Oh, here's the factor 5. And here's a factor 5. And then, of course, if I click now, the 5 will be gone. We find that, and let me put the 5s back. We find the following result. So why? So what we were doing, we were transforming this, right? So e to the power minus 3s times 1 over s minus 1 over s plus 2 is the Laplace transform of this thing. So that's what we get here, u3 times 1 minus e to the power minus 2 t minus 3. We also had the extra factor of 5 over 2, so that's in front of this. And then there's a e to the power minus 2t, which is simply the inverse transform of this. So using the theorem I just showed, I can transform this whole thing to this. And you see that there's a decaying. So for t smaller than 3, we just get a decaying exponential. And at t equal to 3 and larger than 3, then this term will also contribute. What will the graph look like? I can show you. Right? Oh, there it is. The graph looks like this. So when t is smaller than 3, so then this whole term that involves the step function does not contribute. So we just get a decaying exponential. And then at t equal to 3, we get this behavior. And this makes sense because if you look at the system again, we have some charge at the capacitor at t equal to 0, but there's no external voltage because the switch is like this. So what will happen? Well, the capacitor will simply decharge over the resistor. But then you get decay. Then at t equal to 3, we pull the switch and there is an external power source. So then the capacitor will charge again. This will be exponentially. Why? Because as soon as it charges, the voltage over the capacitor will counteract the voltage of the power source. And in the limit, we get a balance where the voltage here is precisely the voltage over the capacitor is precisely 5 volt. When does that happen? Well, the capacity is 1/2. So the charge at that point will be 1/2 times 5 is 5 over 2. And you see indeed in the limits, it approaches here 5/2. So it all works out very nicely. And this is the main power of the Laplace transform. And this is also the reason why it occurs in signal processing so much, because you can very nicely work with pooling switches, which gives discontinuities in your differential equation. But using the Laplace transform and most importantly, using then this theorem, you can deal with those discontinuities very easily. All right. So this is the main content of section 6.3. In 6.4, this will be more elaborated more. So next time we will see more examples of this idea where you have a discontinuous function, and you can still solve a differential equation that involves this discontinuous function by using the Laplace transform. The question, of course, is then how do you, in general, for a discontinuous function, how do you take the Laplace transform? And this we will address next time. All right. This was the story for today. I'll have a quick look at the chat. Are there any open questions? The last page, Jenny, which one in the slides? I wrote the solution. It's also on the, oh yeah, there's a factor 5 missing. This one? Okay, great. I will edit the slides, yes. You don't have to remind me. So are there more questions at this point? A general question by Ashley. That's a good question. The exam will focus on the material of the later lectures. Of course, there are some dependencies where you will use, for example, I assume that you know what a second order differential equation is, things like that. But we will focus on the techniques that we've seen. So I will not ask you to do a power series substitution in one question, maybe as a small part of some other question related to things that we see now, have seen now. But we will focus on the latter part, because the second exam already tested the first part. It will not be proctored. No, it will be the same setup as last time. And so Enrica, yeah, it is not proctored. So it is open book, so you can use the book. And the Laplace table is in there. So don't worry about that. Yeah, I think that's you can just use the book. If you want, I can also put the table in the PDF. But I mean, that's slightly more convenient, of course, because you don't have to know where the table is. But my advice would be just put a post-it at the page of the table, and then you can easily find it in the book. So those are my advice. Okay, if there are not more questions, then I would leave it here, and I wish you all a very good weekend, and I hope to see you all on Tuesday. Okay, see you then.